Hi, and welcome to the fourth webinar in 12D's Industry Solutions webinar series. My name is Lisa Stewart, and I'm the Marketing and Communications Coordinator at 12D Solutions. While we wait for everyone to join, I'll just pop a polling question on the screen. You'll have about 30 seconds to answer about your interest in 2D modelling, and then I'll show the results. Okay, looks like we've got a few different answers from attendees today, and nobody's here under duress, so that's fantastic. Okay, let's get down to business. Our Industry Solutions webinars are designed to provide insights into overcoming challenges in an evolving industry in a more effective and efficient way. We'll keep running these webinars regularly and recording them for posting on our website and on YouTube. Our first 3 webinars are already available online if you missed those. During this live presentation, you'll be able to type your questions along the way as shown on the screen, and we'll answer as many as possible throughout this webinar. At the end, I'll also read out some of the questions to our experts for their insights. Today's webinar on Drainage 2D will be presented by Rob Graham, our resident Water Resources Engineer, with almost 20 years experience here at 12D and over 30 years experience in the industry. We also have Chris Huxley from TUFLOW online with us today to answer questions. Chris is a Senior Flood Engineer within BMTWM with over 15 years experience in the field of flood modelling and floodplain management. In the presentation today, Rob will be demonstrating how to use 12D Model to create a small 2D hydraulic model of a roadway intersection, run the TUFLOW engine and review the velocity, depth and hazard results. The visualization of the results will be in plan, section, and 3D animation. Over to you, Rob.
Thank you very much, Lisa. Good afternoon to everyone. Our Industry Solutions topic today, 2D modeling, is an important component of managing overland flow for serviceability and for safety. During major flood events, it's important that we protect our valuable assets, such as our homes. When we talk about 2D hydraulic modeling, there's several applications that come to mind. The first would be flood modeling. In this application, you can see a river in front of you, and what we would be concerned about here would be the flooding in the floodplain area you see on the left-hand side of the image. In this area, we'd be concerned about the velocities, we'd be concerned about the depths, and we'd be concerned about the rising and the falling times of that flood event. And that's very important when it comes to evacuation planning. Another application of 2D modeling would be something like the dam break analysis. There's many small dams that are in urban areas and in mining sites, and if these small dams were to ever fail for numerous reasons, we would be concerned about what would happen to the effluent and what would happen to the safety of the people that live downstream. Today we're going to be talking about the application of 2D modeling in the urban environment. This is when we'd be concerned about the flow down the sides of the roads, road overtopping, ponding in sag locations. First, let's go back just a little bit to what preceded 2D modeling, and that's the 1D modeling process. The first thing I'd like to address is this concept of 1D. When we refer to 1D, we mean that the velocity goes in a single direction. So when we do 1D modeling, it's up to the modeler to define the flow path. And you can see in this image on the right, these arrows, that is up to the modeler to decide where the water is going to flow down the road. Once we've decided the flow paths, the next step is to cut the cross sections. These cross sections have to be cut at hydraulically significant locations. And this is the essence of good quality 1D modeling, is making sure we have good cross sections. In this example, we've shown a cross section of the sag location in the road. That is the center line here. And what would happen here is the water would pond up, flow across the road, and continue down. And you'd be able to calculate a water level behind that road crest. Now, 1D modeling does a very good job of calculating the water levels along the sides of the roads, and it also does a good job at the road overtopping. However, in the case where we have water flowing down the roadway and we exceed the half road capacity, the water starts to flow over the crown of the road to the other side when the velocity is in the direction of the road and the overtopping is in the opposite direction. When we have to analyze these flow conditions with 1D modeling, at best we have to make some crude assumptions. And this is where we move on to 2D modeling, and it really comes into its forte. Now once again, I'm going to address this question of 2D modeling. When you look at the flood results, you typically look at a 3D image. So you look at this and you say, where's the 2D modeling? If we come back and take a look at how we do 2D modeling, instead of cutting cross sections, we create a grid. So if you take a look at this grid, the water would flow in two directions. It can flow over one side of a cell or the other side of the cell, giving us two velocity components, an x and a y. If we take the resultant vector from these components, we get our velocity resultant that we're looking for in our results. So before, when the cross sections meant everything to 1D modeling, when it comes to 2D modeling, the grid is everything. So yes, the grid is everything. Well, it's almost everything. There's other factors, but if you don't have a good quality grid to begin with, it's going to be difficult to get accurate results. So on the left-hand side, we can see the data train model, and everything looks just fine. When we take elevations at the center of every cell, and we take one elevation for the center of every side, we get what you see here on the right-hand side, where the data train model has been turned into the grid. So what we're looking for, by the way, this was generated from a check file that TUFLOW creates to make sure that the modeler can see what TUFLOW sees. And we can notice a couple anomalies here. First of all, there's a bump. Well, that's not supposed to be there. That's going to impact the flow. So we would go back and look at a data train model to see what's happened. Also, if you take a look here, it seems that our footpath is rising a bit unexpectedly. Another thing we'd go back and investigate. One of the things that we've done when we create the grid is that when we want the water to flow down our gutters, we want to ensure there's a continuous flow path. And we also want to make sure the ridges of our roads are accurately modeled, so the overtopping is done correct. This use of ridges and gully lines is another important part of creating that grid that we'll discuss today. Now, we can't talk about the entire 2D modeling process in approximately a 20-minute discussion. Therefore, these are the 5 points that I'd like to talk about today when we look at them using 12D model. So moving over to our 12D model process, what we see before us right now is the data train model. Now, this data train model is being presented with the visualization, so you can see the things like the grass and the roadway and that sort of thing. And what we need to do now is to take that data train model and turn it into a grid tin. So let's take a look over at a plan view of that same data train model. Step number one, we need to define the extents of our calculations. 2D modeling is a time-intensive process. The computations can typically take 5 minutes to days. The larger the area, the larger the time. So therefore, we want to keep it as small as possible, yet make sure we include all the relevant areas. This includes almost the top end of our catchment, which will work out very well in this case because we're planning on doing rainfall on grid. So let's take a look at how we put this together inside 12D. We're going to come down here and we're going to bring up what inside 12D we call a road flow panel. This road flow panel is a terrific introductory tool to get 12D users and 2D modelers to quickly be able to get flow patterns across our roadways, our intersections, in a minimal amount of time. So the first thing we're going to do is pick that grid, the rectangle that defines the extents, and we can start talking about cell size. Now, we'd like to have the cell size quite small so that we can adequately model our surface. However, if we make it too small, the computational time step will become excessively large. So there's a balance that has to be taken. A cell size of 1 meter would be appropriate for this. A roughness. The Manning's end for the surface will determine the velocities or have an effect on the velocities, and it will also affect the flow patterns. So when we start, we have a default that will be used for the whole area, but of course if we were going to refine the model, we'd add some extra polygons later to have additional roughness area. Moving down to boundary conditions. Within our model, the water has to enter and it has to exit. In this example, we're going to have rainfall on grid, which means we're going to have a constant 100 millimeters per hour falling into this entire area. Now in this example, we are using a constant rainfall, but of course with TUFLOW, you're more than welcome to have historical storms. You can have design storms, and you can also have user-defined hydrographs. But for this example, we'll be doing a constant rainfall on grid. We're going to have it rain for half an hour. For the size of this catchment, that'll allow it to reach a steady state condition so that we can see the flow paths. We're going to take snapshots of the results every 30 seconds. So if we're running this for 30 minutes and taking 2 snapshots every minute, when we're all finished, we expect to have 60 plus 1 start, so 61 time steps of results to view. Now the ground tin. The original DTN that we looked at in the other view, that was a super tin inside 12D, and it's from that we'll extract the levels. Those levels create the grid tin, and that is the grid that I was talking about before that gets sent across to TUFLOW, where we have an elevation at the cell centers and an elevation at the center of the sides. There's several files that will be created during the process. They're all going to be kept together in a single folder here called subdivision. And the format of the files, it's not important for what we're doing right now, but we do have a choice of whether we use MIDMIF or shape files. Now what I'd like to do is also talk about the boundary conditions and how the water leaves, and I also want to talk more about the ridges and the gullies. But the other thing I want to do is get this up and running, because this project will take about 5 minutes to solve. So we'll come down here at this point and say, yes, let's get this thing running, and say, yes, I want to erase the old runs. And what will happen is the TUFLOW engine will get up and running. The very first thing the TUFLOW engine does, which is critical, it reads the data, but then it writes out its check files. One of those check files we were looking at earlier for the grid. And these check files we're going to review to make sure that the grid that's being used is what we expect. So notice that while it's up and running, what I'm going to do is I'm going to switch to another 12D model session. And in this 12D model session, we're going to read in those check files that were created, and we're going to take a look at the results as they progress. So we'll move back down and we'll select that same panel that we selected before, move across to the results, and we're going to choose the TUFLOW log file. When I go and hit the Read Results button, what 12D is going to do, it's going to read the results up to the point that they've been solved, and it's going to import that Z-points check file. That's the grid, once again, we saw before. And that does take a moment. Now let's move this over to the side, and let's go take a look at our result controls. What this lets us know is that at the moment that I hit the Read Results button, 7 time steps had been solved, 12 time steps had been solved. And what I'd like to do also is turn on this extra tick box that says Monitor the Run. What that does is 12D is going to now keep an eye on that other run, and you'll notice it just clicked over to 15 results. So now I know just how far that run's progressed. If you remember my earlier calculations, when that number gets up to 61, it'll be finished. So let's get going. Let's take a look at these check files. When I selected Read Results, it also read in the check files, so I'm going to go back to another 3D view, and I'm going to add on one of my check files called Subdivision, Check, and then Z-points. Now this probably looks familiar to you if you were watching the PowerPoint presentation. And what this is the grid that TUFLOW is currently using to model the flows. And you'll see in here that we had before, there's that little bump in the road. We've got our flow paths across here, the gullies, and you can see here how the center line of the road has been well modeled. So, except for these problems that we already know about, it's looking fairly good. Let's go and take a look at some of the other check files. I'm going to move across to a plan view, and on here I've got some of the road design strings. And what I'm going to do is come across, and I'm going to add on the other check models, except for the Z-points. And I want to take a look, a little bit more detail about these ridge lines. So if I zoom in a little bit closer to the ridge line, you'll see that the side of the cells did not line up exactly with the center line of the road, and it rarely ever will. So what we need to do is to ensure that the side of the cell is raised up to the same elevation as the center of your road. And that's the important aspect of a ridge line. These indicators with the triangles pointing up say that that cell side has been raised. Now the other side, now that we've talked about the importance of having the ridge done properly, is how about the gutters? We want to make sure the sides of our cells are at the same level as the invert of our gutters. And once again, the side of this cell is not necessarily at the same location as the gutter, so we have to make sure that this flow path can be created. And that's what the gully line is all about. So what it's done is it's lowered the level of the sides of the cells to the same level as our gutter to ensure that we've got a flow path. So those are the two very important modifiers to the tin. They're not required, but very important parts of having a good quality tin. Let's start taking a look at some of those results now. I'll go back to the 3D view, and I'm going to add on the results that we've read in so far. Now you'll notice that we've got some results here. Let's add that first. And what we've got is the water surface being drawn, and it sort of looks like a greenish water there. But that coloring is the color by depth. If I move across to our results controller, you'll see that I'm looking at time step 7, even though 47 have been solved so far. So we haven't hit our 60 yet, but we're getting close. If I step along, every time step represents half a minute. You'll see that the water's getting deeper in our sag location, and we're getting closer to overtopping our half-road capacity, so exceeding our half-road capacity. So if I move across a few more time steps, we get to the point here at just after 10 minutes when the water does start to overflow. Now once again, this calculation of when you reach the half-road capacity and exactly where the overtopping will occur is very difficult in 1D modeling and done very well inside 2D modeling. Now I'd like to take a look at some velocity results. So I'm going to move across to a plan view and use this plan view to review the velocities. So once again, I'm going to come up and add on a model that was read in when we said read results, and it's the subdivision results velocity. Let's zoom in a little bit closer to this area, and you can see those resultant vectors, the ones that we talked about in the PowerPoint presentation, and we can see the direction of flow. This is the lowest spot at the sag, if you remember that from the cross section, and you can see that's where most of the water is coming through and flowing down the road. Let's move over to our result controller, switch over to our velocity results, and let's once again step through in time. So we're going farther along now, we're up to 10, and if you remember from our previous one, if we get up to 10.5 seconds, that's when we saw the water just starting to overtop the road. Looks like it actually started at 9.5 minutes. And now we can see that we've just started to overtop. Also, you've probably noticed that the arrows get larger because they're drawn to scale. A 1 meter long arrow is 1 meter per second in velocity. One of the next things I'd like to talk about is if we come down, as I said I was going to come back to talk about some boundary conditions. The default, if we hadn't put a value up here, would to have the water exit on any one of the 4 sides with a single boundary condition. However, if we've got water coming down our roadway on either side, we would like to have different water levels or different boundary conditions for both sides of the road as the water exits our project. Putting in a value of 0.1 here says that it will analyze the cross-section at the edge of the model. And if it finds any channels that are deeper than 0.1 of a meter, it will make a separate boundary condition for them. So we've got separate boundary conditions automatically for both sides of the road. Now if we browse back here, we'll notice that yes, we've hit the 61, unexpected, how about that, 62. Yes, there's one extra one other than we planned for. That last one is the maximum results from the entire run. Well, now that that's finished, let's go and close this project. We're done with it. We only used it just to monitor the results during the run. And we're going to come back to our main project and read in the results there. So now those same results have been brought into this project. We'll go back to our data terrain model. And now what we see inside here with all the visualization is if we go back to our result controller, time step 62, which is the maximums from the entire run. And what we're able to see is the flooding on the 2 sides of the roads, and once again, the overtopping across the center. Now, we've covered quite a bit. Our desire when we started out here was to cover these 5 topics, and I think we've managed to do that. do keep in mind that this is just a brief introduction into 2D modeling. There's much more to do inside 2D modeling and to do inside 12D. So what I would like to do now is to take a look at a few questions and answers, questions that we might have received during the presentation, and discuss the answers for them, or at least our thoughts around them.
Thank you, Rob. I think we've just got time probably for one question today, just looking at the time. Tim from Newcastle would like to know, are there any problems with making the cell size too small?
I'll take this one, Rob. That's a really great question. It's particularly relevant for your urban assessments. And it's actually quite a complex question, although it doesn't sound it. As some background information, the TUFLOW engine uses the shallow water equations for its calculations. So as a rule of thumb, we'd like to advise people to not exceed a cell size to depth ratio of say 5 to 1. So if you have a cell size of say 1 metre like Rob was using, then if your water depths are exceeding say 5 metres, then you possibly need to increase your cell size so you're getting the right representation of the shallow water equations. There's also a limitation in terms of how small you can go, and that has to do with the scaling effects of our subgrid turbulence assumptions. And we typically recommend a minimum value of around about 1 metre to a half a metre. In Salinite, I recently did some validation with some flume tests that went down to a 0.1 metre cell size, which also performed well, but we wouldn't really recommend that small. Generally speaking, what you'll find is that your run times will dictate how small you can go. Obviously, the smaller your cells, the longer your run times. And as a rule of thumb there, if you halve your cell size, your run times will go up by a factor of 8. And the reasoning for that is halving the cell size will give you 4 times as many cells, but then you also have to halve your time step to make a stable simulation. So practically speaking, often that'll be the limiting factor. If you find your run times are taking too long to execute, then you may need to increase that size, and just halving your cell size, doubling your cell size will reduce the run times by a factor of 8, so definitely something to consider.
Okay, thank you very much, Chris. I'd love to get a straight answer for that one. It's appreciated.
We'll just squeeze in one more question. Nick has asked, how are pits accounted for?
Very, very good question. In this project right now that I've shown you, we just looked at the overland flow patterns. As soon as we introduced a pipe system, it's not a difficult thing to do, but one of the optional items we have on here is to specify your drainage model. Then what happens is that each one of the inlets is treated with inlet capacity, whether it's an on-grade or a sag pit, and water is able to go down into the pipe system through the pits, or if it happens to surcharge, it'll come back up to the surface and flow down the roadways. So it's done by having an integrated and coupled 1D, 2D model. Now that'll have to be a great topic for another presentation, and I look forward to doing it. So thanks for asking that.
Wonderful. Thank you very much, Chris and Rob. That's all we've got time for in the live Q&A today. Thank you for all your excellent questions. We'll be answering them individually after this session if we weren't able to get to your question during the live bit. The recording of this webinar will be available in coming days on our website and our YouTube channel. Our next 2 Industry Solutions webinars will be BIM Overview on the 23rd of March and 12D Model Data Management on the 20th of April. Stay tuned also for the launch of our new training webinar series in between those 2 dates. We'll update the website with many more topics in coming weeks and also keep you posted through email and social media. If you need to contact us in the meantime, our details are on the screen now. That concludes our presentation for today. Thank you for attending, and we hope to see you at future webinars.